Ever wondered how a magnetic core supercharges inductance and how it saturates under real currents? In minutes, you'll see a clean μr sweep in COMSOL, then flip on a BH curve to watch the effect of saturation on inductance. Stick around for a neat probe trick to plot flux versus current in one go. Hi everyone, I'm Mohammed and this is High Volts Academy. Today I'll show you how to implement a magnetic core in COMSOL Multiphysics. If you're into Ferrite core inductors and transformers, you're in the right place. Stay with me. We'll start with a linear μr model, then switch to a nonlinear BH model to see saturation in action. In about a minute, we'll sweep μr from 1 to 10,000 and watch inductance climb, then we'll make it realistic with a BH curve. For saving time, as you see, I have created my geometry in 2D, step by step. Let's see my steps. First a rectangle, then another one to form the magnetic core frame. Next, a larger rectangle to model surrounding air. I've also added two symmetric rectangles for the coils or windings. And finally a polygon here, which is the path I'll use to calculate magnetic flux through the magnetic circuit. Okay, let's click build all and our geometry is ready. As you see, I'm using a magnetic fields physics in 2D with a stationary study. For the material section, first we should add the air from our material. Click build in, double click air, and air is assigned to all of our model. For coil regions, here and here, keep the material air. For our magnetic core, because it is a linear material, I'll add a blank material from here. I'll rename it as linear magnetic core and assign it to my core. If you come here, three properties should be set. For the relative permittivity, I type 1. For electrical conductivity, I add a very small value like this one. And for μr, I define a parameter because I want to sweep it later. So you need to come here in global definitions under parameters, μ_r, and for the first simulation I set it to 500, and here you can see the value. Please notice that linear modeling needs only μr. It's fast and simple. Our material section is ready. Let's move on to physics. Under magnetic fields, the Ampere's law is already present. For a linear magnetization model, the magnetization model should be relative permeability, and let the software to recall μr from material definition. Please notice that for a full linear model, 1 Ampere's law suffices for the simulation. Now we need to define our coils. Right click, add a coil. I select my two domains, set my conductor model to a homogenized multi-turn. Select a coil group because they act as one coil. Set the number of turns to 100 and leave all the other things unchanged. Now we should define the reverse current direction. Right click, add reverse current direction and select one face of the coil so the pair is oriented correctly. If you are new to this, watch my earlier video called Model Solenoid in COMSOL. In a second we'll hit compute and you'll see magnetic flux trapped in the core versus air. Okay, let's move on to mesh. I'll keep the physics controlled mesh at normal and just compute the model. What you will see here is the magnetic flux density norm or Bnorm. Notice how magnetic material traps the flux inside the core, which means that the B inside is high and in air it drops very fast. The lines in the air are a stray flux, that's your leakage inductance in circuit terms. Let's quantify μr's effect on the model. For that, come back to study, right click, add a parametric sweep. Click add. I want to sweep μr from 1, which is the air, to 1000 and change my entry method to number of values. 10 values would be enough. I click on replace and then you can compute your model. Here you can select your parameter value. At μr equal 10,000, Bnorm can display values like 7 Tesla. That's physically unrealistic for steel, but it illustrates how the linear model behaves if you force a huge μr without saturation. At μr near 1000, you can see that the Bnorm is around 0.8 Tesla, which is much more reasonable for silicon steel. With μr equal 1, we have only air. You can see that the B value is very small and the field lines largely close in air. Okay, let's see the effect of μr on the inductance of this coil. For that, right-click Results, add a 1D plot group, then right-click again and add a global. Under Replace Expression, Magnetic Fields, Coil Parameters, we have something called Coil Inductance. And the x-axis is set automatically to parameter value, click plot, and you see a near linear rise with μr. As μr rises, the amount of inductance also increases. For example, with μr of 1000, you get a roughly 0.45 Henry in this setup. Okay, now let's make it real. Switch to a nonlinear BH curve and watch inductance flatten as the core saturates. For defining a nonlinear material, come here under Material, under Add Library, AC/DC, we have something called soft iron without losses. Double click it and I assign it to my core and disable my linear magnetic core. Let's get back to setting. If you open your soft iron, you can find two BH curves. The first one called BH curve and the second one effective BH curve. Just as a hint, if you are simulating in a stationary mode or a time-dependent mode, you should use the BH curve, and if you are simulating in the frequency-dependent mode, you should use effective BH curve. Okay, double-click on Interpolation. You can see a table here that defines the BH curve. Here is the H in ampere per meter, and here is the B in Tesla. If you want to see the relationship, just click on plot, and here you can see your relationship. Let me just zoom in. This is the H and this is the B, and here is nearly our knee point, and you can see these black dots which are the points of our table. Here we have interpolation options. If you set the interpolation into linear, it selects the points between two defined values from the linear interpolation, and if you set the extrapolation to linear, it just moves on a linear line in the both sides, here and here. And if you set it to constant, let me plot again, this constant would clamp be beyond the last point in both sides. Okay, I set it to linear, plot, and you can just set your y-axis to log scale to see your BH curve better. Today we'll use COMSOL's built-in table. In a future video I'll show you how to modify or import your own BH curve. Okay, our physics also needs change because we have a nonlinear area. We need another Ampere's law. Assign this Ampere's law to your core, and in the magnetization model, instead of relative permeability, set it to BH curve and let the software to recall the BH curve from material definition. Now we have the coil regions and air linearized and a nonlinear core governed by BH curve. Okay, I want to excite my coil with different currents to see the effect of saturation. For that, I define another parameter IXC for excitation. Come here under parameters, IXC, and I set it for now to 1 ampere. Okay, to see the effects, I come here under the parameter sweep, change my parameter to excitation, and I want to start from 1 ampere in 2 ampere steps to reach 51 ampere. Now let's compute our mod. Let's look at the results. In 1 ampere, we get a B around 1 Tesla in our core, but if for example move to 11 amperes, we get a 1.5 Tesla, and if you push toward 50 ampere, you get nearly 2 Tesla, and you see that B increases much less because the core is saturating. Now I want to see the saturation in a curve. I'm going to plot the average of B versus excitation current. For that, come here under the derived value, right click, under average, select the line average, select your line. In this case, COMSOL average any parameter that you select over this line. Click Replace Expression under Magnetic Fields. Magnetic, I select Magnetic Flux Density Norm and click on Evaluate. Now you get a table. In the first column you have the excitation current and the second column you have average of the magnetic flux density. Click here on Table Graph and you can see these two values versus each other, and clearly you see the saturation effect here, that when the excitation current goes up, the magnetic flux density doesn't improve linear with that and goes under a saturation. Now let's see the coil inductance versus current. Just click on our previous plot. It automatically shows the inductance versus current because of our previous settings, and you can see that at higher currents inductance drops. This is a classic saturation behavior. Now let's put our attention to magnetic flux phi via integration and thickness. In order to estimate the total flux phi, you should integrate B over a surface. But because we are in a 2D model, we have only one dimension. Therefore, we should integrate on a line and multiply it by the outward dimension over thickness. For that, just come under Derived Values, select Integration, Line Integration, select your line and select magnetic flux density. You can see that the unit is Weber per meter because it has been integrated over a line. If we suppose that the outward thickness of our core is 10 cm, I can just multiply my expression by 0.1 meter and you can see that our unit is Weber. Click on Evaluate and Table Graph, and you can see the amount of Weber, amount of net flux in our core versus the excitation current. If you want to plot the flux for any reason versus other parameters, you can just come here under the definition and under probe, add a boundary probe. Here, instead of all boundaries, set to manual, clear your selection and select your line because I want to calculate the flux that goes through this surface. Change the type to integral, and here the expression is automatically norm B, which you get Weber per meter. I can again multiply it by my core thickness and I get Weber. You should recompute your study because in the first study no probe was present. Click on Compute. Okay, now you can use your probe. For example, I want to see my flux versus current. Right click, add a 1D plot group, add global. Under Replace Expression, under the definition, you now can find your boundary probe, and now I just simply plot my flux versus the current, which I get the previous result. But I also can plot the flux versus, for example, core dimensions or any other change in my setup. Keep that probe because next time we'll insert an air gap and compare COMSOL against analytical magnetic circuit model. Okay, that's it for today. We built the geometry, ran the linear μr case with a μr sweep, switched to a nonlinear BH core, and visualized saturation with E, inductance, and flux plots you can reuse. If this helped, like the video and subscribe to High Volts Academy. You can grab the simulation file from the explanation in the description, and if you're new to coils, watch Model Solenoid Coil in COMSOL, which is my previous video. In the next video, we'll add an air gap to the nonlinear core and compare the results with analytical formulas. Stay tuned. See you next